Hi, and welcome to the Chapter 1 Introduction in AP Statistics. Our book is The Practice of Statistics, the 5th edition. There's a newer 6th edition that is on its way, or actually maybe has been released, but I have not seen specific differences that relate to content, so I'm perfectly happy with our 5th edition. If you have a 4th edition, your homework problem numbers are going to be different. So I advise you to make sure that you're looking at the 5th edition that has the pink flamingos on the front in rows. I think the 4th edition also has flamingos, so just make sure you're looking at where it says 5th or 4th edition. So we have a little introductory portion, and I'm going to do Chapter 1 in 3 videos. So the introduction and Section 1 will be in this video. All right, moving forward. So I don't want to read slides to you. I do want to point out things that I think that students often miss when they read the text. You should be reading the text. You should be reading the example problems. You should be reading all of the little boxes, the call-outs that talk specifically about the AP exam. This book was perfectly written for the AP exam. It's the best one that I've found that prepares you for this material, for this test. So if you follow their examples and you use the example questions as the models for how you go about organizing your answers to questions, you will learn exactly what you need to learn to be able to do FRQs beautifully. If you pay attention to their definitions and to their sections where they are asking you to do an extra little thinking about a topic, it will guide you in the right direction to help you understand how to think about AP exam questions, both multiple choice and FRQ. So please make sure you're reading the book thoroughly and doing your homework questions. And those are the 1 and 2 things you can do to learn this material in order to get an excellent grade on the AP exam. Since we have 1 semester to cover it, it's very important that you keep up with the homework and do things on time. And if that is the case, then you will have very little need to study in a massive way for weeks on end at the end of the semester. You will not have time, since we're doing it in 1 semester, to spend weeks and weeks on just studying for the exam anyway. So I advise you to keep up, and you'll do beautifully. Here we go. Really don't like this terribly short definition for the word statistics, but it will do. It's much more than just the science of data. It's the mathematics behind why we can use the processes that we do to understand what data is saying and to use data to make predictions. So we will go into descriptive statistics here in the early part of the course, inferential statistics, where we use data to infer things that aren't recorded, or to estimate unknown numbers. That will come in the later part of the class. So we're going to focus on data analysis here and ways of using and looking at data, not just lists of numbers, but learning how to make pictures with the numbers and organize, display them, and otherwise understand summaries of numbers and patterns in those numbers. And we have to remember that we are the individuals that the data describes and what characteristics of those individuals that we're looking at in order to do that. First of all, we want to make sure we understand the difference between a categorical variable and a quantitative variable. The number one misunderstanding is that people think that categorical variables can't be numbers. So we can place people in categories, and individuals in data sets are not always people. It can be anything that we're studying. It could be, had a student do a project one time to determine if one brand of Oreo type cookies put in more stuffing than other brands. So the individuals were cookies in that case. So individuals can be anything that you're studying. And so when we take down information about them, we could be weighing the cookies and see how much each cookie weighs. And that would certainly be a quantitative variable. We could, if we're looking at a package of cookies and trying to understand characteristics about them, we could put in how many cookies were broken versus how many cookies were whole. That would be a categorical variable. If I was looking at people, I could measure their height. That would be quantitative. I could get their zip code where they live. That would be categorical. Now notice, zip code is a number, but it's not quantitative data. It's categorical because, and here's your ultimate test for a number to see whether it's categorical or not. If you take the average of the number for a bunch of different individuals and see if that average has any meaning. Does the average zip code have a meaning? Well, no, it doesn't, because zip codes are merely descriptive of where someone lives, not a measure of how well they live or any other number. A 0 makes no sense for a zip code, so it doesn't have a scale on which numbers can be compared to one another, where one number is a higher number than the other, and we know how far apart they are. Categorical variables don't have those features that numerical and quantitative variables do. Okay, so here we have an example distribution, which I really enjoy their definitions in this book. When you get confused about something, go back and read the definitions. A distribution, this definition is perfect. It tells us what variables are in a set of numbers and how often those values happen. So that is probably the clearest definition of what a distribution is. So here is a set of numbers talking about the miles per gallon of various car models. So in a table form, we can get certain bits of information. So here in this table, we can see various models of car and their miles per gallon. And we can only really get so much information from a list of numbers. Now, the variable of interest is miles per gallon. If you don't know what MPG stands for, get used to it because they don't explain it, okay? And you can represent this data visually, and here's just a simple little example of a dot plot. If your data set is small, you can do dot plots. You can do dot plots with large sets of data, but you want to do them with a computer and not by hand. Like dot plots with small sets of data because you can do them by hand very quickly and get a feeling for what the data looks like. So in this big chart, whoops, we don't get a feeling for where the data bunches up and where it spreads out. But look down here. Over here we got a bunch of data here between 25 and 29 kind of crunched together, and then very spread out down here on the low end. So thankfully our cars in this list get better gas mileage than these one or two down here below. It really begs the question, what car only gets 14 miles per gallon? Oh, it's a Bentley. Okay, it's a super expensive kind of car you only see with chauffeurs driving. So that I get. Okay. So just very quick example of how a chart, a plot of the data, gives you much more quick information than a mere table or list. Okay, so we explore the data. You can look through individual numbers. You can draw graphs. You can do summaries of data. So here's a picture from the TI-84 screen of various numbers, X bar. Well, that we're going to learn is the mean of the data set. The sum of the data is not a statistic we use very much, although it's in formulas for other things. Pardon me, the sum of the data points squared, that's really only in other formulas. We don't need that one, but we've got Sx and sigma x. And these little x's down here are meant to be subscripts, but this older model of calculator is not very good at displaying subscripts. So we're going to talk about which one of these numbers to use for standard deviation when we get to this feature in a calculator and how to make the calculator do this number for us. N is a data set with 24 numbers in it. So we can do numerical summaries with various statistics in them to help us understand the trend of the data. So understanding the difference between the population you're studying and the sample that you picked from the population is pretty important. And if you don't know, if you can't name the population that you're studying, that you're drawing a sample from, then your study is very poorly defined. So make sure that you can describe, let's say we're studying the GPA of the average student at your high school. Well, the population is every student in the high school. So if you only go and draw samples from senior classes, then you haven't represented your whole population very well. So understanding who your population is helps make you a better sampler, okay? And so here's just a summary of what was in this little section, and I'm going to move on to section 1.1 that gets a little bit more in depth about charts and graphs. And so far all we've seen is a dot plot. Use these learning objective slides as a checklist when you're studying for tests, and make sure you understand what's listed in them. Also the chapter summaries or the section summaries at the end of each section before the homework questions in each section would be an excellent way to review the material and list all the vocab words. Just make sure you're not leaving out concepts when you go to study. So here we're specifically looking at categorical variables, and in this table we had different types of radio stations. So we had radio stations that played country music or that played religious music and so forth, and that's how they divided these up, and they counted lots and lots of radio stations and divided them up into these formats. Now I want you to learn a word here. A relative frequency table is different than just a plain frequency table. We have counts in a frequency table. So how frequently did we pick this kind of radio station in our sample? 1,556 times we picked an adult contemporary station. Versus a relative frequency. Relative means in relation to other categories. So that adult contemporary category was 11.2% of the data, and necessarily the percentages should add up to 100% or close to 100% with rounding issues. And that's fine if it doesn't round perfectly, okay? Down here, this would be the total number of radio stations in our sample. And they didn't specify on this screen anyway if it was the whole country they chose these stations from, but we can understand the data in this chart without necessarily knowing who our population was because we didn't have to sample the data. I will say knowing if this was just from one state or one country or the whole world or whatever is a helpful piece of knowledge, however. All right. Sorry, I should hit all these buttons as I talk. Let's make sure. Okay. See, you go too far sometimes. I apologize for the formatting in this slide. This is a legend that is so small you can't read it, and I just couldn't get the formatting to go any other way. This is a newer version of PowerPoint than my slides, apparently. Okay, so frequency tables are still just lists of numbers, and so we like pictures. And here's a sample of a bar chart, or bar graph, or a pie chart. And if you could actually read the items at the bottom, these would be very helpful. So in our pie chart, we've got our different category labels here, the adult contemporary, the religious, the oldies, the different types of categories. On the left axis over here, we have frequency counts. If we were able to read everything that was this tiny little print shows, these would be good representations of the data. Although the pie chart is somewhat limited, they were kind enough to put the percentages here from the relative frequency diagram. And so that helps us read the pie chart better. Without those numbers, this is only a semi-helpful graphic, even if we could read all these categories, it's big enough. So we'll learn about some charts are less helpful than others, okay? So this is where we talk about graphs that are actually helpful, but graphs versus graphs that misrepresent material. And things like if you have to draw a bar graph, you make the bars equally wide because your eyes judge the area, not the height, on a subconscious level. And so if some bars are wider than others, even if they're shorter, they're going to misrepresent the proportion of data in that category. Don't use little images for pictures because, again, you're not representing the area, the proportionality of the percentage or count of items in one category versus the other. There are media outlets that are famous for this, and some good examples in the textbook for using pictographs, and so we will not be using pictographs here. So I've got some examples of some bad graphs, okay? Some of them are famous. This one happens to be famous. 2012 presidential run, this pie chart was very interesting. And I'm wondering if you've noticed right off what the problem with this chart is. I just don't think that, what is this, 193% in this pie chart. I'm wondering if somebody got fired over this because that one has just gone so big in the news that it's just funny. There are other examples of very poorly done charts and graphs online. This is one. Okay, so this one right here on the right, can you tell what's wrong with this one right here? So this is not a pie chart with its obvious error in the last one, but can you tell me how this graph is misleading? So stop and pause the video if you have to think about it for a little while. Once I tell you what it is, it's going to jump out of you, and you'll see that people use it everywhere all the time. So hopefully you pause this and stop to think about it a little bit. This is showing the Times, which is in the New York Times, versus the Daily Telegraph and their sales volume. And it looks like the Times is more than doubling the sales for the Daily Telegraph. They're really stomping them down into the ground. But if you stop to look at the scale, the bottom of the scale is 420 thousands. Okay, so the scale is given up here thousands. And the top of the scale is 490 thousands. There is no zero on this scale. So you can't really say that the Times sells twice as many newspapers as the Daily Telegraph like you are tempted to do because this scale doesn't go down to zero. So that is hugely misleading. The real difference between them, not quite 40,000 newspapers, is less than 10% of the sales volume. for either paper. So this huge distance between the top of the Daily Telegraph and the top of the Times only represents 10% difference in sales. So the Times, this may have in fact been in the Times, and is making it look like they're a lot more popular newspaper than others. So oftentimes that not having a zero on the scale will be used to make things look shocking in their changes. So here we have this tiny little bar in first quarter of over 100 million people in the U.S. now receiving some form of federal welfare. So here's how many people in first quarter of 2009. And this looks like it has grown 3 or 4 times but big by the second quarter of 2011. But really, just look at the scale. So here we're about 97 million. Up here we're almost at 108 million. That's not 4 times the number of people, but the graph sure makes you think like that. So make sure you're avoiding these bad problems with badly drawn graphs. And the don't do it comment is about pictographs. All right. One other comment we want to make is scales. Make sure the scales go down to 0, and you'll be able to make graphs that people can use with appropriate proportions. Okay, we're going to get into two-way tables and talk about marginal and conditional distributions. And these are two things that people get mixed up very, very much for each other. So we're going to have a two-way table that takes 2 different kinds of categorical variables and gives you different pieces of information about them. So in the book you read about this sample, hopefully you read this already, where they ask young adults the question, what chance do you think of becoming rich, that you have of becoming rich in your lifetime? And so they record their output here, and they were kind enough to give us totals. If you're ever given a two-way table without totals, realize that to answer any questions about them, you're probably going to need those totals, both row totals and column totals. And each of the total columns should add to the same number if you've done your addition right. So you can be an accountant and check that if you have to provide your own totals for something. But the difference between the numbers that are bolded here, the total row and column, and the table total down here in the corner, and the actual data. Okay, so each of these little boxes is called a joint in the graph, and the joints are not bolded, and that's the actual data, and the totals are in bold here, and tables don't always bother to bold the outside margins. And so I want you to maybe draw yourself lines here to make sure that you don't mistake 1083 for a number of data points that represent individuals. So those individuals are already represented in these 2 joints. This is just the total of those together. So make sure you're reading these right, and you'll avoid most of the mistakes people make here. The other mistake people make is they can't tell the difference between a marginal distribution and a conditional distribution. And the marginal is where we compare totals to the table total. So it says how to examine a marginal distribution. You're going to look at the table and you're going to compare row or column totals to the table total. Okay, so I like their examples here. Here are marginal distributions. Notice the denominator is always the table total here. And notice the numbers in the numerator are always row or column totals. See, the 194 up here is here, and there are 4% of respondents to this survey that think they have almost no chance of ever becoming rich. On the other hand, we have 29.4% of respondents thought that they had a good chance of becoming rich in their lifetime, and 22% were almost certain. That's a very high number in my opinion. But marginal distributions are always taking numbers from the margins only. There are no numbers coming from the joints in marginal distributions. Okay, so you can just get percentages of people in the different total columns. Then you can go and draw a chart based on the percentages. That helps you draw a bar chart here, since this is categorical data. All right, so when you want to look at the relationship between 2 numbers, 2 joints in the graph, in the two-way table rather, you are going to pick a column that you're interested in and compare it to the row or column total. So you can make side-by-side bar graphs or segmented bar graphs with these, and on occasion they ask you to draw these on FRQs, so pay attention here. The difference. Okay, so conditional distribution. This is saying if somebody is in one particular category, what percentage of them are in another category. So here for males, if somebody is male, what's the percent chance that they think they're not going to get rich? And so notice the 98 is one of the joints. The numerator is a number from the joints, just the actual data points. The denominator is a number from one of the total columns. So conditional says, okay, first we're just looking at males. And that's where the 2459 comes from in the denominator here. We could do the same thing for females. We could also do the same thing and make the denominator the total column over here and say, for people who think they have a 50-50 chance of getting rich, this percent of them are male and this percent of them are female. So we're actually pulling one from each category, comparing a certain, in this case, gender to a certain choice in the survey. So that's what makes a conditional distribution. And then they can do both male and female here and create a segmented bar chart so that you can get a really good visual on how to compare males and females. So I want to show you something in the book about how to answer questions when they say compare. So look at our question from the book here. It says, based on the survey data, can we conclude that young men and women differ in their opinions about the likelihood of future wealth? Give appropriate evidence to support your answer. Very typical AP question here. And so you would be given, a lot of times they don't make you do your own calculations. Sometimes they hand you this, but if they didn't, you'd have just the table to go by and you'd have to come up with these percentages yourself. And so notice the structure of this answer gives an opinion and backs it up. That's the evidence part. They didn't just say a yes or no question. They never will. Even if they accidentally phrase one as yes or no, they don't mean it to be just yes or no, or I think that this is true. They always want the evidence, whether they actually say give the evidence or not. Okay, so it says we suspect that gender might influence a young adult's opinion about the chance of getting rich. So we'll compare the conditional distributions of responses for men alone and for women alone. And so I do this table. And it didn't say you had to draw a chart, but this is a good way to support what you're saying. But here's the meat down here, the evidence. So they didn't just say more men think that they have an almost certain chance of getting wealthy than women. They actually gave the numbers, and there's the money. You got to give them numbers when you're saying that this is more than that. Notice how they insert them in the little parenthetical expressions. So I think this would have been a fine answer even without the side-by-side graph, bar graph over here, but listen to this part. Based on the sample data, young men seem somewhat more optimistic about their future income than women. Men were less likely to say that they have some chance, but probably not, than women, and then they give the numbers. This is here. That's very important. They mentioned that men were less likely to say this than women. So they didn't just say men, on average, have higher answers where they think that they have a better chance. They didn't summarize it with words. They stated greater than, less than, they gave the numbers. This is what they're looking for. So this is your first taste of how thorough you have to be in the answers to your questions. And notice that they did not address this answer as if the people who were reading their answer knew anything about statistics. They were very explicit, explained everything. You are to assume that your audience, when you're answering statistical questions, is an audience of people that don't know statistics and don't understand anything about it. You're expected to talk to them. You're not talking to a room full of statisticians and implying things. You have to state them explicitly. I'll repeat that again and again throughout the course, I'm sure. Okay, so relationships. We want to know if, when it comes down to it, we want to know if being male or being female causes you to have certain answers in this situation. We often want to cut to the chase and say, does A cause B? We are nowhere near saying that A causes B in this class. So all we can talk about at this point is an association. Are gender and opinion on this question associated? And what that means is that if we didn't know what gender somebody was, would they have the same likelihood of having the same answers? And when we look at here and we see a much larger piece on the female graph of people that have, this was not the no chance, this was the some chance question. Much larger percentage of females said some chance of becoming rich than men. And it looks like about the same percent that said 50-50 for men and women, but here the good chance is wider than that for women. So, we gave the answer before had specific numbers. It was a much more clear answer than what I just said, and I hope you recognize that when I was saying it. But here, I think it's a safe assumption to say that men have a generally more positive outlook on their chances for being rich in their lifetimes. But we cannot say being male caused them to have that opinion necessarily. Okay, we'll have a test for where we can judge things like that later on, but right now we can say it seems that gender is associated with people's opinion about their future prospects for wealth. Alrighty. Strong association, that implies that we have a way to measure that one association has a stronger relationship than another, and we're nowhere near that either yet. So there's a phrase here that they've thrown in that they're not defining, a lurking variable. There could be other explanations for why the genders are different here, but we certainly haven't gotten any information that would tell us what that is. And we're only allowed to speculate based on personal life experience a very small amount in this class. There are very few opinion questions here. So be careful about inviting in too much personal background knowledge, because sometimes that just leads you down a path that doesn't help you. All right, here's a summary of what we went over in this section, and please make sure you're picking up on these details as you read through your material and answer your questions. Thanks so much for listening.